Hey, this is Pradeep. I'm a senior data scientist with experience in natural language processing and deep learning. Lately, I've been venturing into the field of generative AI. So, as you might know, recently there's been a surge of models coming from Google, Meta, and even OpenAI and Microsoft, for example, models like GPT, DALI from OpenAI, Llama from Meta, and even Gemini and Bard from Google. So all these models come into under the fold of generative AI. So these models are called generative models because they try to generate new content out of their own pre-existing knowledge base. So for example, GPT generates text and DALI generates images. And if you've heard of Sora, which is a new model from OpenAI, it also generates video. Given a simple text prompt, it's able to generate an entire video, although it's not perfect as of yet. But yeah, these models are able to pull off something only humans were capable of until recently. So they try to generate new things out of their own pre-existing knowledge. So that's what they do. And in today's topic, I'll be going over just the large language model aspect of it, where these large language models like GPT, for example, Llama and Gemini, all these models are called language models, where they try to do one thing only, where they try to generate text, and they try to understand and generate new types of text, whether it be English or multilingual, depending upon the training data that it has seen. The language model tries to generate new sentences. So I'll be going over briefly what a language model actually is. I'll be going over some limitations of the language models that exist as of today, and I'll be going over a technique called RAG, which is Retrieval Augmented Generation, which is very interesting and further enhances the applicability or usability of large language model in a real world use case. And I'll be going over a simple use case or a sample case study that I've built, which leverages these techniques called RAG and also a large language model as the foundation. So first we need to understand what a language model actually is to understand how these models like GPT and Gemini are able to create new sentences, make up information as they go along, right? So to understand that, first I want you to think of how would you fill this or complete this sentence. I woke up early, I got ready and made a dash dash, right? How would you kind of complete the sentence or fill in the blanks? It could be any number of things. Some possibilities include a cup of coffee, a plan for the day, a to-do list, for example. So it could be any number of things based on the context and speaker's preferences. It differs. So that's how the large language model actually learns. What it does is a step called language modeling, where the model is learning to predict the next word. So, given a small input sequence like this, it tries to predict the next word that comes into the sequence. It's done through a technique called mass language modeling and next sentence prediction, depending upon the model architecture. But yeah, these models are based on transformer based models. So, I won't be going into the math behind how these models are trained, but just at a high level, all you need to know is given a small input sequence like this, I woke up early, got ready, and made a dash. It first generates a probability distribution and all the potential words that could come after this, and then we for example, as a simple uh, uh, arc max kind of a thing, we just pick the word with the highest probability and we put that in. Once we do that, we have one more word in the sequence, and auto-regressively, we take this entire sequence again and try to predict the next word again. So by doing that, we might get to a sentence something like, I woke up early, got ready, and made a cup of coffee, for example. After that, the model generates an end of sequence token, which is a special symbol, which means that the generation is complete and it doesn't generate anymore. Given a small input sequence, contextually it builds up just by predicting the next word again and again. It's able to entirely generate new sentences. And these large language models, through their massive amounts of data that they're trained on, they're able to become very good at predicting the next word in any sequence. So coming to large language models, these are actually deep learning based models, and they're based on transformers, which is a model introduced by Google in this paper called Attention is All You Need. And I highly recommend you to take a look at this paper so that you get all the context you need. And the math behind this model is also very interesting if you just have a couple of hours to just understand and apply this model in your own work. So these large language models have been shown to have a meaningful understanding also. So just by training on this massive corpuses, including books, maybe movies, it also has Reddit, it has just internet data of all sorts. They've refined this data, and then they've gone through multiple stages of training. For example, one is just simple pre-training, where they've fed this entire corpus to the model to just do mass language modeling, so that the model tries to predict a word in the sentence. So one specific token within a sentence is blanked out, for example, and then the model, using the context data and a mechanism called attention mechanism, it's able to understand the context and then predict what the word has to be. And just by doing this, it's able to understand what a language is. It's able to generate the patterns to understand a specific language. And given that massive amounts of data, it's actually able to generate new sentences as well when it comes to the decoder part of the transformer architecture. So going forward into GPT, right? So what is GPT? You might have heard of Chat GPT a lot, but what does GPT even stand for, right? So GPT stands for Generative Pre-trained Transformer. So generative means it generates sequences through auto-regressively, and it does next word prediction. As I mentioned just before, given a set of inputs, auto-regressively it just uses consecutively built up sequences to then predict the next word in this entire sequence again and again. By doing that, it just tries to generate new sentences directly. And P stands for an important step in the process, which is pre-training or pre-trained, wherein this LLM is trained on a massive amount of data from internet. One specific source is called Common Crawl, which contains a lot of internet data, and they have even used data from books and all sorts of other sources. So leveraging this massive amount of data, the model is actually able to learn the language, understand the language, and even generate new sentences within the same language, and even be grammatically correct, right? And finally, the T stands for transformer. So transformer is actually the backbone of GPT or all these large language models that are coming through. This neural network architecture was introduced in 2017 by Google, as I mentioned. And the crux of this model is attention mechanism, which is very interesting. And I highly recommend you to take a look at the paper to understand more on it. So yeah, next we go a little bit into the limitations of the large language models that exist today. Even though there is a huge hype behind these large language models, there are a lot of pitfalls and blockers or kind of disadvantages of the models as they exist today. So one is hallucinations, where these models kind of hallucinate or make up information as they go along. So given an entirely new topic, they can just produce coherent text which is understandable but which might not be factually correct. So they even try to gaslight the users into believing the wrong information sometimes. If the user doesn't validate, they would never know, and they might even believe the information coming from these models, which is not entirely true sometimes. And to learning, right? These large language models, they might seem like they're learning. If you talk to ChatGPT, it might seem like it remembers the flow of conversation, but actually it's all done with just prompt trickery, I would say, or API trickery. So all the previous conversations that you've had are just fed back into the model as a prompt, and the context is given of the conversation, and then the model, just using entire context, tries to again do a chat completion and generate the next sequence in that order. So what it's just doing is, it's a stateless model. The large language model is actually stateless. It doesn't remember the previous interactions or the previous inferences that it has done, but just using some prompt trickery, they are able to make it feel like it has knowledge or memory. And custom data, right? The large language models as they exist today, they can't really utilize custom data. For example, if you want to use your own database, your own internal documentation, right, to make the large language model work on that and pull information from that, uh, the simple foundational LLM can't do that, which is a uh, huge drawback. Right. One more huge thing is a token limit. So all these models, whether it be GPT-4 or Gemini, they all have a token limit, the specific token limit. Beyond that, they can't even work properly. So, the, whatever context or the information you can feed to the model has to fit into that token limit. If not, the model simply won't understand. For example, if you want to feed an entire book book to the large language model and ask it to just generate a summary out of it, it wouldn't work. Directly right off the bat, it wouldn't work. And there is a transparency issue. For example, even if the model generates a correct answer, we might not be able to point out where the source of that information is, even though the LLM is pulling off its pre-existing knowledge coming from its pre-training. We can't explain to the users how this answer came about, right? For example, in domains like pharma, insurance, and various other sensitive domains, this doesn't fly. They need explainability, but actually, because LLM is a transformer or a deep learning based model, they generally perform like black boxes, and we can't get behind the scenes. And one more issue generally with LLMs is ethical concerns. Like there is a risk of having bias in the model. Even the answers generated could be harmful, although this is mitigated by a huge extent by a technique called RLHF, which was introduced by the OpenAI folks. It's called reinforcement learning through human feedback. So what they've done is they have uh, different types of criterias where these human evaluators would judge the output of the model and give the feedback to the model, and it actively learns to not give out harmful information, give out very structured and helpful and useful information. So the model is aligned of sorts, so that the outputs are aligned to what we expect from the model. Even then, there is a risk of sometimes the model behaving abnormally. And one final and huge limitation of a large language model is anyone can't train their own model. Because even if you have to train a model like Llama 2, which is a 70 billion parameter model, even though it's huge by today's standards comparing to GPT-4, Gemini, and all these bigger models coming through, it's still a much smaller model. Even that model takes 1 month to train, just one iteration of it, to get one final version of that model, and it takes an estimated of 20 to 40 million dollars of training cost. So to deal with all these limitations, this is where RAG comes in. For example, RAG stands for Retrieval Augmented Generation. So what it actually does is when we need to generate a new generation from a large language model, we look up information from our own database. We use that information, pull that information, and use that as context to the prompt that we're going to give to the large language model. And then finally, the large language model, using the context and the custom data that we've given it, it generates its own response. So what this tends to do is there's multiple benefits to it. One is we can use real-time context, that is dynamic data can be used. Instead of LLM having to rely on its own pre-existing and out-of-date knowledge, it can use the latest and relevant knowledge. It can even use private data. For example, we can use our own databases, our own set of documentations to actually make the large language model work on our domain and our application. And one more interesting thing that this tends to do is it grounds the large language model on the knowledge base that we have. And what this tends to do is, in practice, it mitigates the hallucinations through prompt engineering and through doing retrieval augmented generation. It mitigates the kind of hallucinations that we generally see with just LLMs. And we can even provide links to the source material, because we have utilized our own information to generate the answer. We can even provide the source information. We can link to the source information and say that this is where we have pulled the information from. So this even solves the problem of having explainability to some extent, right? And we also see that latency and performance doesn't take a huge hit when we use RAG as opposed to fine tuning or training our own models. And finally, I want to go through the RAG flow as it exists, right? So there are two parts to it. One is indexing, where we just ingest all the data. So it could be different types of data that we're working with. It could be PDFs, it could be Excel, it could be any types of multiple types of data. Actually, it could be web-based pages as well, URLs, JSONs, whatever you name it. We are able to extract text from it, and then we after that we split all the documents into smaller chunks, because as I mentioned, there is a token limit to these models, and then we can't have any arbitrarily large documents being fed into the vector store and thereby to the large language models later on. So we just split those documents into smaller chunks, and then we create embeddings out of it. So what embeddings are basically just high dimensional vectors which kind of have a semantic representation of the original text. So these are vectors or sequences of numbers which just encode the information present in the text into a vector format. So in the embedding space, what this allows us to do is by embedding similarity search, we are able to pull information that is similar to it. For example, if there is a new user query coming in and we just need to uh, retrieve the information related to it, we just do an embedding similarity search and are able to pull all the nearest kind of vectors and thereby pull all the nearest or most relevant chunks of text, and then we utilize that in the generation aspect. So what this allows us to do is it's not just a simple search, it's not just control F. We are able to semantically search for information through the power of embeddings and then use that as the context. So to complete this flow, we're just going to do it offline generally, where the indexing happens. We store all the information necessary into a vector DB. Some examples include ChromaDB, VV8, and Phase, or even Azure Cognitive Search, which is a very mature and stable kind of a vector store and semantic search mechanism. And finally, once we're done with the indexing, it generally happens offline or it happens as a background task. If we have to do with dynamic data, then it generally happens as a background task where we update the vector store in the background and then the retrieval continues in the foreground. So next we do the retrieval and generation. So this is where the actual magic happens, where whenever a user query comes in, we retrieve the necessary information from the vector store that we have. We retrieve the information present, and then we use that as the context to the prompt. We have the prompt augmented with the necessary context, and then we pass this on to the LLM. And once we do that, we have an answer which is very much grounded and it has the relevant information and knowledge required to answer the specific question coming from the user. So that's the power of RAG. And coming to the small use case study, right? We have built a small application called AI Tutor. So what this enables us to do is it's a combination of RAG and the large language model GPT-4 or GPT 3.5. We could use either one, and it just helps the learners to understand a bit more. So it's a simple chatbot at this stage, but yeah, I'll go through the demo in a little bit and hopefully it makes sense. So this type of AI tutor would be capable of offering interactive lessons. For example, instead of having the learner go through the content themselves, we can have this chatbot which kind of goes through the material for the user with them, and it can generate quizzes, it can give instant feedback, it can adjust its teaching material through intelligent prompt engineering. We can dynamically adjust and optimize the students learnings, right? This is the same flow as a simple RAG material, right? We upload all the materials for the application, we do the indexing first into Chroma as a vector store, and then we initialize the chat application where the simple conversation continues, where the learners could ask their questions, and using RAG, using the necessary material, it pulls the correct information and answers the users based on that, and then the chat continues. That's a simple flow for this application. So this is the code base for the application that I talked about just now. It's called AI Tutor, where the backend of it works with primarily LangChain. So LangChain is the orchestrator which creates the chains. It does the conversational it enables memory to the large language model. It has a lot many other functionalities that we have not explored in this specific project, and highly recommend you to check out LangChain documentation to understand more. And the front end for this application is just using Streamlit. Streamlit is a very good package to build a UI at a very quick pace using small or lesser number of code, lesser lines of code actually. So using Streamlit and LangChain, we've built this application, and also use the actual model at the backend is GPT 3.5, and I'm using Azure Chat OpenAI, the API to power that. You could also use Chat OpenAI directly, which also provides the access to GPT 3.5 as well as 4 or many versions of the models directly from OpenAI itself. For that, you just need to go to platform.openai and get the API keys necessary to access the APIs and then get the chat completions. So going through the code base itself, it's a simple application where we get the files uploaded from the user, and then we build the knowledge base. This is where the indexing step comes in within the RAG framework. We use the files, we split them using just LangChain splitters, and then all the splits are then stored into a vector store. I'll just go into the actual utility functions themselves. So there is something called a recursive character splitter coming from LangChain itself, which splits all the docs into splits, and then we utilize this to create a vector store and then store them into our vector DB. So for the vector DB, we're using Chroma and Hugging Face embeddings. We could even use OpenAI embeddings. It's up to you which embedding or which embedding model you use. I'm just using the open source Hugging Face embeddings that they provide from Hugging Face. Uh, these embeddings and the splits go into the chroma, and then we first convert all the splits into embeddings, and then we store them into the vector store, and this vector store is returned back to the conversation memory. And we initialize the LLM over here. We could either do Chat OpenAI directly or even Azure Chat OpenAI. I have access to Azure Chat OpenAI, so through the Azure portal, we can set it up and then get all these credentials that are required, and uh, the API keys as well. And all these different environmental variables are stored in a separate folder, a separate file called .env, so that there is no leakage of sensitive information. And it's a good practice to do that. And all those .env variables are loaded into the current environment using a package called .env. By just doing .env.load.env, we are able to load all the environment variables necessary from that specific file. So going into it, it's just going to be the final chain is just a conversational retrieval chain. If you go into LangChain documentations, you can understand how this works in the background. But what it does is it takes an LLM and it uses the retriever, which is actually the vector store. It uses the retriever, and we can also provide it memory. So the conversational memory, it can kind of store and then dynamically pass it on to the large language model. So as I mentioned, right, there is a prompt trickery that we could do where we can give it memory by just storing the information, storing the previous conversations, and then repeating back to the large language model. That way we are able to run a conversational flow within the model. So we just use this chain coming from LangChain, and this enables the entire workflow for us. And then there is another chain called quiz chain, but yeah, I'll be just demoing the conversation and Q&A solving chain for today. And there is a the handle user queries utility function, which actually takes the messages from the user and then gets the completion from AI and then displays it all nicely into the Streamlit application itself. So let me get started and run this. So we are now able to see the screen, right? So this is the sort of UI we have built. Where we first get the option to upload file. I'm uploading something called, maybe let me upload a small document about generative AI itself coming from Stanford. And then we can select the model temperature as well as given a small slider so that we can select the temperature. So what temperature is kind of, you can think of it as a parameter to the model, to the large language model, determining how creative or how deterministic or rigid the model tends to be. So because this is a AI educator, I'm going to leave it at 0, where it's going to be as strict as possible and not very creative when generating its sentences or the information. When it gives the responses, it's not allowed to be too random, for example. So yeah, we have built the knowledge base. As you can see in the backend, it has created a vector store and it's stored as a chroma object. Now it gives us a small message saying, "Hi, I am your AI tutor. What topic would you learn about today?" So I can just say something like generative AI. Since I've fed it information regarding generative AI, I'm just saying generative AI. So what it does is now it has pulled the information in the backend and then gave me the answer. So let me go into the logs itself. So there is a system message. Through prompt engineering, we've given it a small system message saying that you're a smart AI assistant and you can use the context to give a good answer to the learner. And if you don't know the answer, you should say you don't know the answer. What this does is it mitigates the hallucinations that come from the large language model. This is the simplest way to mitigate those hallucinations and do constructing good prompt chains and constructing good sort of prompt engineering pipelines. We are able to make the LLM perform in ways very custom and behave in a controlled manner, how we want it for the application, basically. So to actually generate this, it has actually pulled all this from the Stanford document that we've given it. It has gone through the retrieval phase where it has pulled chunks of index 9, 10, and 15, as you can see, and it has used all that information to answer this specific question. So even the previous context that hi, I am your AI tutor, and then the response that I gave, that is generative AI, everything went into the prompt to go into the large language model, and then the answer came out comes from this entire RAG chain. And I've also given a small information regarding how many tokens are being used. So as you can see, the prompt, the chat, doing RAG within the prompt only, there's a lot of tokens, and the completion tokens, which are these tokens, are just 94. But for the cost aspect, right, all the tokens count. So that's where we are seeing that it's approximately $0.003 for this specific prompt that has gone through. So I can even ask it to generate something specific like generate a quiz on generative AI, short, right? Now it should go through, again, pull the necessary information, and then through the power of the LLM that's running in the background, it can generate a small quiz for us, and then it can take us through that flow. So yeah, as you can see, there's even a short quiz on generative AI. It asks what is generative AI, and it even gives multiple choice questions that it's formatted itself. And then we can use these quizzes, and you can even answer this quiz because we have conversational memory. It remembers the previous output that it has given, and then it would even try to give us feedback on how we have done. So iteratively and interactively, we can interact with the system, and as you can understand, it has a lot of applications. Just this RAG based application, right? In various domains, it could be used in multiple ways. So yeah, that about concludes the demo today, and I hope you've understood a little bit about the power of LLMs and even the limitations of it, and how a technique called RAG helps in kind of improving on the pre-existing uh, impressive functionalities of the large language model itself. So yeah, thank you.